Section 1.8 talks about Introduction to Linear Transformation. Linear transformation is something we're going to be playing with for a while, and the name pretty much gives it away. Linear referring to kind of like a linear equation in which you have a linear relation. So if we talk about R1, so linear transformation, if we talk about 1, if you give me the vector 1, I can pretty much in R1 get anywhere on that space. So multiply this by 0, I'll be right there at 0. Multiply it by 1, I'll be at 1. Multiply it by a half. I can pretty much trace the entire space by simply that 1. If I want to span R2, R2 is 2 dimensions. If I want to span that, basically if I want to be able to be anywhere on that, I need 2 vectors. I need the vectors 1, 0, 0, 1. Any point you want me to get to, I can use a combination of those to get there. If you say go on 3, 2, I'll say okay, multiply this one by 3 and multiply this one by 2. That will be 3, 0 plus 0, 2. That would be 3, 2, or simply 3 to the point that you want. So I can get anywhere I want. You could get it and trace this entire vector notation. The book uses this loosely. I'm going to stick with this. So I could trace any point in R2 by using those 2 vectors. And if I want to find R3, I can do that too. Well, guess what? I need the following 1, 0, 0, 0, 1, 0, the following vectors. And any combination of those 3, I can get anywhere I'd like to be in R3. And in general, when I want to find R sub n, actually it's right there. It's pretty much the identity matrix if you're talking about an n by n. If you're talking about n by 1, depending where you are, you want the 1 to match and everything else will be a 0. Now, we call these vectors E1, E2, E3, depending on the space, we call them the standard basis. Basis is a massive deal that's coming our way for Rn. For now, we're just going to touch on it, leave it alone, and then come back to it pretty soon. These vectors, E1, E2, all the way to En and Rn, are termed basis vectors because all other vectors in Rn are expressed in exactly one way as a linear combination, meaning multiple of them. Any vector that you pick in R sub n, I could figure that out by taking a multiple of these vectors up there. And I could figure out what that is. Just like we did here. If you want to take the point 7, 3, 1. So move 7, 1, 2, 3, and 1. Well, hey, multiply the first by 7, the second by 3, and the last by 1. And there it is. If you want to be at 0, 2, 3, well, that's easy. 0, 2, 1, 2, 3. Well, multiply the first one by 0, the second one by 2, the third by 3, and add them together. And these are called the weights on these vectors. And I could pretty much be anywhere I like on this space. So those form the basis, which means they can take me anywhere, or any point that you pick or vector you pick in that space, I can write as a combination, linear combination of those. Now, when we talk about a function, if you input a in a function, right? That if you input a, you should get f of a. They call that here b. So they say if you have the point a, b, that's a function. The input is the domain. The output should be the range, but here they call it codomain, which is the same thing basically. In some books they talk about, again, this is the image and this is the pre-image. So the image happens after you input something, and the notation, a function maps a point x into f of x or simply b. Same traditional function, but here it has slightly different uses. If t is a function, so t is what's taken me from the domain of A to the codomain or range B. F is what doing that. Now we're going to use a transformation. We say if t is a function with domain R sub n and codomain R sub n. So this is the domain, this is the range, so to speak. Then we say t is a transformation from Rn to Rm, or t maps every point in the domain into that range, which we denote by T4 transformation. Takes any vector in Rn and maps it into Rm. In a special case, when those are equal, if these powers are equal, the transformation sometimes is called an operator of Rn. That means it takes things and it takes vectors and map it into itself. Now, matrix transformation, this is something that we've been practicing heavily. If I have this system of equations, can't I write this? And can't I write the coefficient of those as matrix, and we call that matrix A? And can't I say x1, x2 all the way to x sub n is that vector right there? Again, we've been doing this heavy duty because we're going to be doing this forever. So we say W equal the transformation of A on X. So we call that transformation T sub A multiplication by A. That's because you simply take X and multiply it by A, and that gives you any vector that you want. And the notation is right there. You take X as a domain, you apply the transformation of matrix A, and you get this W. T sub A matrix A maps X into W. Now here there are a few things to keep in mind. We are inputting X, and the output is AX, which is W. And as I get to the first problem, I'll elaborate on what that means. Now we want to set few things. If 0 is an m by n matrix, so all the entries are 0, then of course the transformation of 0 should give you the 0 vector times anything. And the identity, if you have I, which is a square matrix, if you apply the identity, transformation of the identity on any matrix, you should get it back. That shouldn't change the value, because we know that 0 times any non-zero vector is 0, and I times any vector is the vector itself. So this is the identity operation, and this is the 0 transformation. This is going to be something we're going to look for later on. Now, theorem 1.8.1 is talking about what does it mean to be a linear transformation. 4 things you have to show, but then 1.8.2 pretty much summarizes it. So first you check that 0 is in there. If you multiply a vector by k, if this is linear, it should move up front. And if you take the transformation of the sum or the difference of two vectors, it should be the transformation of the first transformation of the second added or subtracted. Instead of doing all of that, it's sufficient for you to show that we have a linear transformation is take that transformation on constant times a vector, and that should be the constant times the transformation, and take the transformation of the sum of two vectors, that should be the transformation on each added. If you could show those two, then that would mean this is a linear transformation, basically linear relation. Now a standard matrix, something very simple, but we're going to find if the transformation on matrix A takes Rn into Rm, and transformation on B takes Rn into Rm. Notice that transformation, we're talking about a linear transformation. Our matrix transformation, if you set transformation of A on vector x equal transformation on x with matrix B, for every matrix for every vector x in R, then A must equal B. What this is showing you, this is showing you that this is a one-to-one correspondence, meaning you could go forward and you could go backwards. So that means there's only a single transport. If you have a linear transformation, it should be the same regardless. You can't do it one way and get an answer and do it another way and get a different answer. If it's linear, it should yield the same results every time. And if you want to find the standard matrix, which what we're going to find in almost every problem, of a linear transformation going from Rn to Rm, that's given by simply, you want to find A, take the transformation applied on E1. Remember, E1 is 1 and a bunch of zeros. E2, that's 0, 1 and a bunch of zeros. And if you apply it and put those in each column, then you will figure out what A is for that linear transformation. As I do examples, I'll point that out. Now I want to get one idea out of the way, which is a bit confusing, but let's make sure we understand that. So find the domain and codomain of the transformation. Notice the transformation. You input an x, that's the domain. The outcome is ax, which is the codomain. So if matrix A happened to be 4 by 5, right? So if I have 4 of those and 5 of those, if I'm going to input x, what must x be for this to work? Don't the inners have to match? Doesn't that mean that the input has to be 5 dimensions? So this transformation maps any vector x, which is in R5, into a vector w. When you multiply those out, you're gonna get 4 dimensions. The outcome is a 4 by 1, isn't it? So the outcome is the range, or the codomain, that's what they call it. And the input is the domain. So again, let's look at this vector right here. If I have 5 by 4, if I multiply 5 by 4, this is A. So again, recall, this is the transformation. The transformation is taking any vector you input and multiply it by this A. What must x be? X is the domain. X is the input. I must input what? 4 by 1? So that must be in 4 dimensions. And the outcome, isn't the outcome 5 by 1? Which means the outcome, the codomain or the range, is R5 and the domain is R4. Here they match, so the transformation takes any vector in R4 and maps it to into W, which is in R4. And here, if you have a vector that is, if you have a matrix that is 3 by 1, that means you must multiply 1, right? So this maps R1, which is R, which is the domain. And it's gonna, transformation is gonna map any vector in R1 into R3, which is the codomain. And I'll point this out as I do few examples. Now, majority of the first set of problems, just getting used to this. Find the domain and codomain of the transformation defined by the equation. Well, if I really want to figure this out, I am inputting x. If I write this here, can't you say this right here is 1, negative 4, 8, negative 1, 4, 2, negative 3, 2, negative 5? Isn't that 3 by 3? Isn't that x1, x2, x3? So if I say that's ax, wouldn't you say that x is 3 dimensions? And the outcome happened to be 3 dimensions as well. That's the outcome, right there, W. So here it doesn't make a lot of difference. Probably it's not very clear, but here, if I rewrite this, wouldn't you say this is W1, W2? Isn't that the outcome? Isn't A 2, 7, negative 4, 4, negative 3, 2? And aren't you multiplying that by x1, x2, x3? Isn't this 2 by 3? And this is 3 by 1. So isn't the input three dimensions? And what's the output? What's the codomain? Isn't the codomain 2 dimensions? If I take this matrix and multiply it by any vector in R3, isn't the outcome 2 by 1, which is 2 dimensions? And that's the idea. If I look at 6, the same deal. Find the domain and codomain of the transformation. Now they're giving you all the different combinations. You could see this. I went ahead and pretty much wrote it that way. Well, isn't this AX? The input, which is the domain, is this vector is in R2. The output, which is the codomain, when you multiply this out, isn't that 2 by 2? Isn't the output going to be 2 by 1? That's the range. So here you map R2 into R2. And how about here? Well, here the same deal. The domain, that is 3 dimensions. And in this case, the outcome is going to be also R3. All right. Excuse me. If I get to 8, I'd like to know what's the domain and what's the range. Find the domain and codomain of the transformation, T, defined by the given formula. Well, what are you inputting? Aren't you inputting R4? And what's the outcome? Isn't that R2? And how about here? What's the input? The input is R3. And the output is how many unknowns are there? Isn't that 1, 2, 3? They match, right? I, J, and K. So I get domain and co-domain or range. How about the next problem? How about number 10? Well, how would we do that? Let's see. If I look at problem number 10, the input is what? R3. The output, what is that? How many is that? Isn't that 4 by 1? So domain, codomain, again, I'm not going to keep providing that. So they're not asking us to do much here. We're going to find a few things first, but for now, can you tell the domain and the codomain? Now we want to talk about this standard matrix. Let me remind you really quick what that is. A standard matrix is this matrix A that allows that transformation to happen. Basically, what do you multiply X with to get W, right? So here, if I'm looking at number 12, can't I say W1, W2, W3 equals, isn't that negative 1, 1, 3, negative 2, 5, negative 7 times x1, x2? This is W equal AX, and we're looking for the standard matrix, which is A, and there it is. So what do you think it is here? 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 1, 1. That would be the standard matrix for this transformation. That's what you multiply X with to get W. And how about if I wanted to go to number 14? Well, I'm going to rewrite this really quick as 2x1 minus x2, x1 plus x2. And what would that be? Wouldn't that be 2, negative 1, 1, 1 times x1, x2? and the transformation on a 2 dimensions gives this. So doesn't that make this the standard matrix? And again, something that we're going to find. For now, they're giving us everything. We just have to read it out. And how about in B? What do you think that is? If I look in B, if I'm going to write this, again, keep in mind what this works. This is really 1, 0, 0, 1 times x1, x2. There's A. Again, you could write them this way or you could write them this way. If I get to the next one, well, the first entry will be 1, 2, 1. The second will be 1, 5, 0, and the third will be 0, 0, 1, x1, x2, x3, and there's my A again. And that's what I'm looking for, the standard matrix for this operation. And what about here? Again, that's a lot of examples, but I want to make sure we speak the same language before we go on and do something else with it. If I really write this, that is 4, there's 3 of them, right? So that's how you write it. 0, 7, 0, and 0, 0, negative 8, that would be A. And by now, hopefully, you're really comfortable with this language. Again, this is something that we're going to keep on coming back to. For now, let's make sure we understand it. And let's look at number 16. 16 takes a slightly different direction. Not a whole bunch, really. But they say, find the standard matrix. What do you think the standard matrix is? You're mapping R4 into R2, meaning the input is 4 of them, and the output is only 2 of them, right? So what's A? Wouldn't you say A is 2, 3, negative 5, negative 1, 1, negative 5, 2, negative 3. So this is the transformation standard matrix. They say, okay, find the standard matrix we did, defined by this. Then compute. Can you compute for me what's T of 1, negative 1, 2, and 4? Direct substitution. If I'm going to go by direct substitution, that would be what? That would be 1 for x1, so that's 2 plus 3 times negative 1 minus 5 times 2 minus a 4, and that will be W1. And I'll get 1 minus 5 times negative 1 plus 2 times 2 minus 3 times 4. So what is that? 2 minus 10, 14, 17. 17, that's negative 15. That's W1. And W2 will be, let's see, the negatives 12. No, 12. This is 5, 9, 10. 10 minus 12 is a negative 2. So there it is. That's by direct substitution. And by matrix multiplication, what does that mean? That transformation takes x and maps it into ax, right? Well, if you take x and you map it into ax, a is 2, 3, negative 5, negative 1, 1, negative 5, 2, negative 3, multiplied by x. And what's x? 1, negative 1, 2, and a 4. So this is 2 by 4, and this is 4 by 1. The outcome is 2 by 1. Do you see how the input is 4 dimensions? You input 4 of those, and you get the outcome is a 2 by 2, a 2 by 1. Well, let's see. How does this work? Don't you take this multiplied by this, and what do we get? We get 2 minus 3 minus 10 minus 4, and to generate the bottom, we use the bottom. And how does that work? We get 1 plus 5 plus 4 minus 12. And do you notice that's the same thing as what we got up there? Negative 15, they're right here, and a negative 2. And of course, this is a lot simpler than what we're doing, well, which is why we're going to go backwards on the long one. But that's not as simple as it sounds. Here's another transformation. Find the standard matrix. Well, if you want to find the standard matrix of this transformation, this is the input x1, x2. The output is what? A would be, in the first we get 2, -1, and then 1, 1. Isn't that A? Isn't that the standard matrix for this transformation? And if we want to do this directly or do it by product, now I'm going to take this and put it on the side really quick. So if I want to apply the transformation directly as it is, what's t of -2, 2? Well, that's simple. That is what? That is -2 minus 2 and -2 plus 2. That is -4, 0. And if I would go ahead and say, okay, what is AX? Isn't that what the transformation of A does? Takes X and map it into AX. That is 2, -1, -1, 1. And if I multiply that by -2, 2, the outcome is 2 by 1. And what would that be? -4. Oh, wait. Oh, yeah, I messed up. When you put -2 in there, -2 times 2, that's -4. That's a -6. So here we get -4 minus 2, which is -6. And here we get 2, -2 plus 2, which is 0. And that would be W1, W2. There. So again, we're showing that, it doesn't matter how you do this, you get the same results. One is always nicer than the other. If I apply t sub 105, for x1 I put a 1, that's a 1. For x2 I put a 0, that's 0 minus 5, that's -5. And then I'll put an x2, which is 0. Now what's the matrix here? Matrix A would be 1. There are 3 of them, right? 0, 0. Will be 0, 1, -1, and 0, 1, 0. And if I multiply that by 105, can you guess what we're going to get? 1 plus 0 plus 0 is 1. 0 plus 0 minus 5 is -5. And 0 plus 0 plus 0 is 0. And there it is. Let me shift things. So I did a bit of shift. I have to do a bit more. What do they want here? Find t sub a. What t sub a of x? That's simply ax. So what do they want here? If you find ax, isn't that simply -2x1 plus x2 plus 4x3? Isn't that 3x1 plus 5x2 plus 7x3 and 6x1 minus x3? You could line them up, you could not, it doesn't matter. Again, we're just getting used to all of this language that we're going to use back and forth. Okay, no matter how much I adjust, I still have to show it. And here, what would that be? What would be ax? Well, wouldn't that be -x1, x2, 2x1, 4x2, and 7x1, 8x2, and there it is. So that's what the transformation look like every time. Okay. Now we get to a bit of fun. And we have 2 of those. Let's get the first one out of the way. It says, use theorem 1.8.2 to show that T is a matrix transformation. Now, forget that it says that theorem. If we want to use it, we're going to stick with not the first theorem, always the second theorem all the time. So we're not going to stick with this. That's a lot of steps. We just have to do this. We have to show that if you take T of the sum of 2 vectors, that's the individual sum of each. And if you take K times the vector, that's the same thing as multiplying the entire transformation by u. So if I take two vectors, let's say we take u and v. If I take, in this case, t of u plus v, that would be what? Well, let's see how that works. That says you're supposed to take x plus y, so that is u1 plus v1, sum of the first two. Okay, no wonder it's not working. I messed up. It's 3 dimensions. I need one more. Sorry about that. Right? There's 3 inputs, x, y, and z. So this says take what? Take u1 plus v1, right? And plus u2 plus v2, right? The I and the j component. This says take the j component, u2, and the third, u2, u3, plus v2 plus v3. And this one says just take the I component, u1 plus v1, right? And if I rewrite this and rearrange them, isn't that u1 plus u2 plus v1 plus v2? And for the second, I could say that is u2 plus give me a sec. It should be u2 plus u3. And v2 plus v3. And as for the last, can't I say this is u1 and this is v1? Again, remember, if you're taking the ij components, you could only get the I to the I, the j to the j, and the k to the k. And wouldn't this be t of u plus t of v? So that shows. And if I take the transformation applied on ku, let's say, wouldn't that be t into, there's u right there, so that's ku1, ku2, and ku3. Based on the transformation, that would be what? That would be ku1 plus ku2 and y and z, so I and j and k, ku2 plus ku3, and then the I component, which is k of u1. Wouldn't you say this is k multiplied by u1 plus u2, u2 plus u3, and u1? And wouldn't this mean that this is k times the transformation on simply u? And there it is. We just proved that this is a linear transformation. I want to try it on BL as well. If I let u equal, here there are 2 dimensions, u1, u2. Now I'd rather use a and b, I know students do, but in this book they really stick with those. V equal v sub 1, v sub 2. So if I take the transformation applied on u plus v, wouldn't that be transformation on u1 plus v1, u2 plus v2, right? And what is that based on? Doesn't that go backwards? Wouldn't that be u2 plus v2, u1 plus v1? Now, wouldn't you say this is u2, u1, and v2, v1? Isn't this t of u, and this is t of v? So that's the first condition is satisfied. Now, if I take t applied on k times u, that would be t applied on, and there's u, that will be KU1, KU2. And that would be what? Well, backwards. KU2, KU1. Based on this, you swap them. Isn't that K into U2, U1? Wouldn't that be K times the transformation applied on U? And if those two are satisfied, we conclude that this is a linear transformation. And how about something like this? Well, use theorem again. The question, is this a linear transformation? Here they're saying, show it's not. Well, let's say we're looking at this and seeing how it works. If I take U to be, well, here both of them don't work. Even the constant doesn't work, and I'll show you really quick. But let's say U is U1, U2, and V is V1, V2. If I take T applied on U plus V, wouldn't that be T applied on U1 plus V1, right? U2 plus V2. And what is that based on this? That's the I component. That's U1 plus V1 and U2 plus V2 plus 1, right? I could say this is U1 V1 and U2 V2. The problem comes with the 1. If I put a 1 right there, I can't add a 1 right here. So you could say this is T of U, yes, but this is not T of V because I need a 2 for that to happen. You could try the K as well, that doesn't work. And here the same deal. If I look at here, let U equal U1, U2, U3, 3 dimensions, and let V equal V1, V2, V3. If I apply T on U plus V, that is T applied on U1 plus V1, U2 plus V2, U3 plus V3, comma. And based on this, it will be the I, it will be U1 plus V1, the J, U2 plus V2, and the square root of U3 plus V3. Okay, and I could say this is U1, add to it V1, and U2, add to it V2, but we have a problem. The square root of U cubed plus U3 plus V3 does not equal the square root of U3 plus the square root of V3. So I can't split that up, so that doesn't work. Therefore, this is not a linear transformation. And the last problem I want to work on, the problem before the last, I lied. Show that this transformation, show that the transformation define the matrix operation in R2, but not for 1, 1. Okay, well, if you take the transformation and you get the 0, 0, right? Well, let's say we take x to be x1, y1, and y, let me think really quick. Okay, let's say you have a point, and point B to be x2, y2. Okay, if I apply t sub x1, y1 plus x2, y2, wouldn't that be t sub x1 plus x2, y1 plus y2? And that would be, in this case, 0, 0, which equals 0, 0 plus 0, 0, which is t of x1, y1 plus t sub x2, y2. That works. And if you take t sub k times x, y, right, or x1, y1, that would be t of x1 times k t sub kx1 ky1, and that would be pretty much 0 0, which is k times 0 0, and that is t sub xy times k, because 0 times any number is 0. But if I go for the 1 1, again, I'll notice I run into trouble. If I say, let's take t of x, y to be 1 1. If I take t of x1, y1 plus x2, y2, those two vectors, I'll get t of x1 plus x2, y1 plus y2, and that would be, in this case, 1 1, which does not equal t of x1, y1 plus t of x2, y2, which is 1 1 plus 1 1, which is 2 2. And since that is not equal, this is not a linear transformation. So we're going to stick with those two identities of that theorem. Now the last part, it's really also straightforward. Again, getting used to that language. The image of a standard basis vector for R3 is given in the linear transformation. We're mapping R3 into R3. Find the standard matrix. So this is what they're saying. They took T applied on E1, E2, and E3, and this is what they got. This is I'm sorry. This is what they got. So if we take T and apply it on E1, E2, E3, isn't that A? Isn't that the theorem that we had? Way up there. Where did, oh, right there. So if they already did that work for us, again, later on we're going to do all of this work. For now, they're kind of giving you the question and the answer. So wouldn't you say A would be simply those columns, 2, 1, 3, -3, -1, 0, and 1, 0, 2? And if you want to take Tx, right, find Tx, isn't that 2, -3, 1, 1, -1, 0, 3, 0, 2, and x is 3, 2, 1, and what would that be? 3 by 1, you'll get a 6 minus 6 plus 1, that's 1. You'll get a 3 minus 2, which is 1, and you'll get a 9 plus 0 plus 2, and 11. And that's what the transformation does, and there it is. And that's pretty much it for this section as well.